Welcome to Module 6, Lesson 21, Mathematical Area Problems. Okay, so before we get into this with our opening exercise, which we will do in a second, just wanted to let you know the idea here is that we are going to be using area models, and with those area models we're trying to make an explicit, like a very overt connection between area and algebraic expressions. Okay, now that may not be so obvious right from the beginning, okay, but as we move along, I'd like you to try to notice that, and at the end it'll become clearer as we get more explicit with this idea. Okay, so again, we're going to use these area models to make this connection between area and algebraic expressions. Okay, so it's a real nice way to kind of combine what we've been doing, throughout this entire 7th grade, and kind of tie it up. And again, it'll help you as you move into your grade 8 year and beyond. So, with no further ado, let's go ahead and get to our opening exercise. Okay, here's our opening exercise. So, Patty is interested in expanding her backyard garden. Currently, the garden plot has a length of 4 feet and a width of 3 feet. What is the current area of the garden? And I won't insult most or probably all of you because I know you understand how to do this. Okay, all we need there are 2 figures here. We have 4. It's a 4 by 3. And therefore we're going to have 4 times 3, which equals 12 square feet. Okay, 12 square feet. All right, but we're going to now work on adding pieces. Okay, so we're going to extend or expand this garden plot. Okay, so Patty plans on extending the length of the plot by 3 feet and the width by 2 feet. Okay, so extra 3 feet in length, extra 2 feet in width. Okay, so what I'd like you to do as we as we start getting into this portion is to go ahead and grab some graph paper. Okay, we've got a piece of graph paper in the back of your binder, and let's use that. And I'll be back in a second. I want to show you. We'll take a look at it here as well. Okay, so if we know that Patty's planning on extending the length of the plot by 3 feet and then the width by 2 feet, okay, we can just, of course, just add to that. Okay, so we have a length of 4 right here, so she's going to do that plus 3. So if we added 3 to that, that's going to be 7, and then we're going to multiply that by, and we're going to add another. We're going to add another 2 feet to the width. Plus 2 there, and so that's going to be 5, and that's going to equal 35 square feet. Okay, so the new garden area would be 35 square feet. Now that's easy enough to do, okay, and hopefully you had no problem with that. But with C here, and this is where we're getting into this kind of this connection now between area and algebraic expressions. I'd like you to go ahead and draw a diagram if you haven't already. Okay, draw a diagram that shows the change in dimensions. Okay, and as it expands, and then the diagram should show the original garden as well as the expanded garden. Okay, so I'd like you to go ahead and give that a whirl. Try it out, and if I'm going to do it as well. And if you have trouble, and again, what I really love for you to do is get that graph paper going. Okay, get that graph paper out and use that graph paper to do it. Okay, so go ahead and give that a whirl and come on back and we'll look at it together. Okay, so using my graph paper here, I mapped out my the original garden plot right there. Okay, and as we know, it was 3 feet by 4 feet, which is actually not 12 feet, but 12 feet squared, or 12 square feet. Okay, so that's our original garden. And if we want to go ahead and expand it out, we'll go ahead and expand it. She said she expanded the length by 3 feet. Okay, and that's the length that way, 3 feet, okay, and then the width by 2 feet, okay, so expanded that. So here's our expansion. So we have our original garden plot here, okay, right, and then our expanded garden here. Okay, so there's our expanded garden. So that's how those two compare. Now if we go ahead and find our dimensions, now we have our new garden, like we knew already, is 5 feet by 7 feet, which of course is 35 square feet. Okay, 35 square feet there. Okay, now we have a letter D, and what D asks us here is, based on your diagram, can the area of the garden be found in a way other than by multiplying the length by the width? Okay, so if you look at this, is there another way to calculate or find the area other than multiplying the length by the width? Take a look at that and see what you think. Well, if you went back to this diagram here, you might have noticed something. What we could have also have done, we could have actually figured out the areas of these separate regions. Okay, so we actually had here, so this is a 3 by 3 region here, so this would be 9 square feet there. This is actually a 2 by 3 region here. I mean, sorry, not 2 by 3, 2 by 7. So this is going to be 14 square feet. So if we add all these, 12 plus 14 is 26, plus 9 is indeed 35 square feet. Okay. So yeah, so another way, an alternative way, would have been to find the you find areas of separate regions. Okay, separate regions. All right. So based on your diagram, further here on letter E, based on your diagram, how would the area of the original garden change if only the length increased by 3 feet? By how much would the area increase? How much would the area increase? So if we go ahead and take a look at that, if only the length by 3 feet, and that's this area right here, if you notice right there, okay, and that's just taking into account the length. So now we would have had a 7 by 3, okay, which would have given us a 21 square feet, 21 square feet, all right, which would have been an increase of just 9 square feet. So this would have actually been plus 9 square feet if we just increase the length. Okay, so let's remember that 9 square feet there. So, and then the next one, the next question, of course, is going to deal with probably the other direction. How would the area of the original garden change if only the width increased by 2 feet? Okay, so if we go ahead and look at that, take away all of this here. Now we're looking this way. I'll have to make an extra different line now, so I have to go here, here. Okay, so whereas that was 14 feet, but now we're looking at a 5 by 4, which is 20 square feet. Okay, and so that would have been actually been a plus 8 square feet. Okay, that direction. All right. So now what I'd like you to do is go ahead and complete the following table with the numeric expression, area, and increase in area for each change in dimension of the garden. Okay, so we have the original garden with length of 4 feet and width of 3 feet. Okay, so you're going to go ahead and put in here, you're going to put 4 feet and then 3 feet. Okay, And then the area, right there, 12 feet squared, 12 square feet. Then the increase in the area of the garden, well, that doesn't apply right there, okay? So go ahead, just in that fashion, go ahead and complete the rest of that table. And come on back. Okay, well, let's go ahead and complete this, and it's probably pretty easy, but I just want to show you the way I did it here when I went and put the dimensions here. When the original garden with the length extended by 3 feet and the width extended by 2 feet, I put those in, as you see it, in parentheses here. These are parenthetical statements here, okay? Because I'm adding, just to show that I'm adding 3 to the original 4 and then 2 to the original 3, okay? And you probably got the same thing here, because we had done that already, increased by 23 feet. And then, and if you didn't do it this way, I'd love for you to go ahead and make that adjustment. And here's the last one, the final one there. Okay, because you can see we are actually increasing only the length there, only the width there. Okay. So, with that done, will the increase in both the length and the width by 3 feet and 2 feet respectively mean that the original area will increase strictly by the areas found in parts E and F? If the area is increasing by more than the areas found in parts E and F, explain what accounts for the original increase. Okay. Now E and F, of course, refer to back here, right here. Here's E, 9 square feet, and then F, 8 square feet. So if we go here, they're talking about these two. Okay, so it says, will the increase in both the length and width, okay, respectively, mean that the original area will increase strictly by E and F? So if we looked at this, E plus F, that's 9, if only increasing the length gave us a plus 9 feet, 9 square feet, okay, and then only increasing the width gave us another it was 8 square feet. Okay, that a total increase there is 17 square feet. Okay, but we are looking at here at, if you notice, 23 square feet of increase when they both are. So there is a discrepancy here. There is a discrepancy. When we increase both at the same time, we add 23 square feet. But when we increase one at a time, those two increases together only equal 17 square feet. So the question is, what accounts for the additional increase? Okay, and I want you to think about that and notice that the difference, 23, good place to start, 23 minus 17, okay, equals 6. So, think in terms, we are 6 square feet of difference between both together and each separately, the increase. So, go ahead and mull that over and jot some thoughts down, and maybe take a look at your diagram, and come on back. Okay, well, I think this using this diagram to answer this question is a great idea, and hopefully you had this in front of you as well. You did as I had recommended, and used some graph paper for this depiction. Okay, and if you did, we can see here, because when we increased the 3 feet in length only, that brought us this way. Okay. And so what it did is it added that 9 feet. So remember, right here, that 9 feet right here. Remember that plus 9 feet? Just going lengthwise. Okay, just going lengthwise. Now, when we added the going down, let me get another color here. When we just added to the width, added 2 feet, okay, right there. Okay, now we have to just change this 14 feet. Let's just take this out of here now, because that's the entire piece. But that added, remember, 8 feet. 8 square feet. Okay, 8 feet square, and that's what's inside of that. Okay, so what we had, remember, we had our, so if we did it only in length, we added 9. Only in width, we added 8, and remember that was at 17 altogether. And what you might notice, what was not accounted for, the little missing piece, happens to be this little piece right here. And guess what? That little piece is a 3 by 2, okay, 3 feet by 2 feet, and it is 6 feet squared, okay? And if you'll notice, this 3 and 2 are very special because the 3 is the increase in length, and the 2 is the increase in width, all right? So when we change just in one dimension, one direction, okay, only that way, only lengthwise, we only moved in this region here. When we moved only this way, we moved only there. And what we didn't account for is where those two measurements, the 3 feet and the 2 feet, actually converged. Okay? Okay, so let's look further. Let's observe some patterns that emerge in each of these area models. Okay, so this one here, you're going to examine the change in dimension and area of the following square as it increases by 2 units from a side length of 4 units to a new side length of 6 units. Okay, so it's increasing by 2 units, well, in both ways actually. Okay, so it's length and width are both increasing by 2 units, as you can see right there. Increase. Okay, so what we want you to do here is observe the way the area is calculated for the new square. The lengths are given in units, and the areas of the rectangles and squares are given in units squared. Okay, so if you take a look at that and look at the way they are given, they're actually, you can see here, it just says 4 times 4, for example, 2 times 4, 2 times 4, and 2 times 2. Okay, there's actually no real number in, well, not real, but of course they're real numbers, but there's no area numbers given there. Okay, so we haven't changed it, because this of course would be 16 square units, right, if we were to do the multiplication, but we're not. So the idea here is just take a look at those and observe what you see. So here we go. So A, based on the example above, draw a diagram for a square with a side length of 3 units that is increasing by 2 units. Okay, and then show the area calculation for the larger square in the same way as in the example. Okay, so you're pretty much going to create another one of these here, but this time you are going to draw a diagram for a square with a side length of 3 units that is increasing by 2 units. So it starts at 3, increases by 2, versus this one that started by 4 and increased by 2. Okay, so you're going to pretty much do the same thing. So draw your own depiction of that. And again, graph paper is a great place to do it on. So going back to this one here, example 1, just for a second, just to show you how we can actually calculate the area a little bit differently. Okay, again, more or less algebraically. There are a couple of ways. This area, so to calculate the area of this extended square, okay, the 6 by 6 square, we could say that it is 4 plus 2, okay, and that's coming from here, 4 plus 2 and 4 plus 2. 4 plus 2 parentheses squared, okay, so we could put it like that. So 4 and then again that would be in units squared would be our units we would use there. Okay, in this case, all right. So 4 plus 2 in parentheses squared. Okay, we could also do it as the sum of all of those different subsections. Okay, so we could have it as 4 times 4 plus 4 or 2 times 4. We can actually we have 2 of these 2 by 4s, so we can actually write it like this. Even we could do 2 times 4. Okay, because we have 2 of those sections plus 2 times 2. Okay, so here's another way we could calculate it. Right, and we did all these calculations. For example, we have 4 plus 2 here, which is 8. Okay, and 6. Okay, and then 6 squared, of course, equals 36 units squared. Okay, and in here we have 4 times 4 equals 16. 2 plus 4 is 6, times 2 is 12, and then 4. Okay, so 16 plus 12, 28, 32. What did I do wrong? Let me see. 6, 12, 16. Oh, 2 times here. Sorry. It's got to be 2 times this one. Yeah, but that's, this is 8. 8 times 2, this is 16 here. Okay. And then 4, and then we have our 36 units squared as well. Okay, so yeah, 2 different ways to express this, the area of this extended square algebraically. Okay, so yeah, I just wanted to show you that because I'd like to actually talk about that in terms of this here. And let me go ahead and just march this back. So I want to do this a little bit all at one time. So what I've done here is I've gone ahead and extended this 3 by 3, okay, this original 3 by 3 square right there, and I've extended it by 2 units in length, okay, and that little region there is going to be represented by 2 times 3, and now we've extended it by the width, another 2. Now we have 2 by 3, and then we have our last section, is that section there, 2 by 2, or 2 times 2, and of course we have created a 5 by 5 new square region, okay, and that's this region here, okay, and we can compare that region compares to this other, our original region, which is right here, okay. All right, so again, now we can, again, I'm not sure if you've done this yet, but you can pause and do this for yourself if you'd like to go ahead and show your calculations. Again, one way we could do this, calculate it, is the extended purple square here would be 3 plus 2 in parentheses, okay, squared, and that would be units squared, of course, okay. So 3 plus 2, of course, is 5. 5 squared is 25, so it's 25 units squared. All right, or we could do it as the sum of all the different regions, and again we have 3 times 3, and then we had 2 of the 2 by 3s, and then this plus, of course, and then plus 2 times 2, and then we have 9 plus 12 plus 4, which is going to equal 25 units squared as well. Okay, so different ways to depict that, or to calculate that. And just something to recognize in these two examples. If you do notice, this one region right here is the 2 by 2, and we increased both dimensions by 2 units. We're left with that 2 by 2. Over here, again, we did increase by 2 units, both dimensions, and we're left with a 2 by 2. Okay, something just to consider. So here we go. B is going to ask you now, again, another example of this, and help us get further, closer and closer to understanding or making this connection between this area process, these area models, and algebraic expressions. Okay, so here you go. You're going to go ahead and you're going to draw a diagram for a square with a side length of 5 units that is increased by 3 units. Okay, so 5 by 5 increased by 3 units in both length and width, and then show the area calculations for the larger square in the same way as in the example. Okay, so we're going to go ahead and do the same, do it the same way that we've been doing it. Okay, so go ahead and give that a whirl. Okay, so let's take a look at how this this pans out. So first I have my 5 by 5 original square, extended by 3 in length, and then 3 in width. Okay, and those would be you know, 2 separate transactions there. If we looked at those, we had this one here. Remember we talked about that, right? We got that. That would be the one just increasing the length, just increasing the width. Okay, but in this case we need to increase both. Therefore, we need to extend. And again, that little piece here is kind of our little secret to everything in the end here is that little bit. Okay. Anywho, so if we go ahead, and this is what we have, and of course now we have a new square, which is now 8 by 8, of course, and that's 64 units squared. And again, a couple of ways to calculate. Algebraically, we could have 5 plus 3 squared, okay, which is 8 squared, which of course is 64 units squared, which is correct. Or it could be sum of the regions, 5 times 5 plus, whoops, you notice that we always, with the square, we always have these 2 regions that are similar. 2 3 by 5, 5s plus a 3 by 3, and this 25 plus 30 plus 9, which also equals 64 units squared. Okie doke. Okay, so this letter C here is going to ask you to now generalize the pattern for the area calculation of a square that has an increase in dimension. Okay, we're talking about squares now only, all right? Okay, square a little bit easier to work with here. Okay, so let the side length of the original square be A units, and the increase in the length by B units to the length and width. Okay, so use the diagram below to guide your work. Okay, so you're going to generalize the pattern for the area. So take a look at this in terms of variables A and B. Okay, and let's and then go ahead and come up with some generalized formula. Okay, so generalized formula. All right, so give that a whirl, see what you come up with, and then come on back and check in. So looking at this this example here, where we're trying to generalize using variables, we can just compare it to what we've been doing prior. Okay, we had all of this going on. You know, you notice what we had. We found 5 plus 3 squared. Okay, and you can see 5 plus 3 squared because it's 5 plus 3 times 5 plus 3. Okay, so if we just looked at it in those terms, oh boy, here we go, I did that again. Oh my, oh my, oh my, oh my, oh my, oh my, oh my. Okay, here we go. Okay, yeah, so we have a plus b squared. Okay, and that's the same as the other one saying 5 plus 3 squared. We have a plus b squared, which is generalizing now. We're coming up with a formula because we've been doing it the same way every time, but we have been using very specific numbers. Now, of course, we're getting into non-specific, we're getting into variables, which are going to allow us to plug in any number we would like. Okay, so, oops, didn't mean to do that quite yet. Oh, wait, Boom, 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 boom. Okay, now that, of course, is the same as that, all right? And because what we are doing, we are actually multiplying a plus b, right here, a plus b, and we're multiplying that times a plus b, which is over here, okay? So these two are, in fact, the same expression, okay? The same expression, all right? So, moving forward, we could even express it in this way, as you remember, when we took the separate sections. We had a squared, which is a times a, and then we had 2a times b, which is ab, and another ab, two ab's, and then we had a b squared, which is also b times b, which is how we did it before, and that is actually the same as this, because that a squared now, taking just this a squared, and turning these two ab's, instead of 2 times a times b, we've just made it 2ab, and then we have b squared plus b squared. Okay, and this is all, of course, these are all units squared. Okay, whatever answer comes out of that, it'll be expressed as units squared. Okay, so we are going to see, and you're going to see very soon in algebra, very early in the year, next year probably, how this can turn into that. Okay, and these are expressions and are formulas that you will be using extensively. Okay, so getting your first little glimpse of these right here, right now. Won't give you too much information now because I'll save that for next year, and hopefully you have something to hang your newfound knowledge on. Okay, so this example 2 here, Bobby draws a square that is 10 units by 10 units. He increases the length by x units and the width by 2 units. So go ahead and draw a diagram that models this scenario. Okay, so you're going to draw a diagram just in the same fashion as these here. Okay, but using these values and of course paying attention to the fact that we have a variable here. Okay, so go ahead and draw that. Okay, so here we go. I've drawn my 10 by 10 original square. Oh, I didn't mean to do that second one there, but my 10. Let me take that off there. Okay, so I started off here with my 10 by 10. That's my my original square. Okay, and then I extended it by 2 units in width. Okay, 2 units in width, and then x units in. I keep doing 2 wrong pauses here. So, and then x units in length. Okay, and you can see that right here. So, I know how much here. Not sure here. Okay, so I have thus I have my variable. And if I go ahead and plug these in, this is what they've done here. And again, maybe you have done 10 squared instead. But if you would, just go ahead and put the actual number in. So that's 100 because 10 times 10. And then we have 10x. Okay, so we have 10 times x. 20, which is 2 times 10. And then 2x, which is 2 times x. Okay, so using this diagram now, we are going to go from this area diagram to an algebraic expression. Okay, so what I want you to do then now here is this b right here, and it says assume the area of the rectangle is 156 square units. Now find the value of x. Okay, find the value of x. How much? So what we're asking here is how much was this square extended in length? How much was it extended in length? We're going to solve for that x. Okay, so what I'd like you to do is go ahead and create that expression. Okay, and all we need to know is that the actual area of this new larger extended square, okay, is 156 units squared. Okay, so what is the value of x? Okay, go ahead and give that a whirl, see if you can summon up all of that we did so long ago, and come up with an answer. Good luck. Alright, so here we go. Our initial expression would look something like this. 156 equals, okay, or is the same as 100 plus 20 plus 10x plus 2x, okay, because we are being told that the entire area, this entire new square, is 156 units squared, okay. Therefore, we know that it's going to be the sum of all of those, and this is just like what we did earlier in this lesson, okay. It's going to be the sum of all of those, so when you add up all those, they should be the same. Therefore, we go step 2, and what we're doing here, if you remember, the term or the process we are using here is called combining like terms. Okay, we've combined our numbers and we've combined our variables there. Okay, and of course we're trying to isolate x. Okay, isolate the x. Our x happens to be on the right side now. Not a big deal. Okay, and again, to get rid of this 120, we need to add its inverse, or just subtract. In this case, do the same to this side, and we end up with 36 equals 12x, or 12x equals 36. And that, of course, we handle this way, again, by multiplying by the multiplicative inverse here of 12x, or by simply dividing by 12 both sides, and that's what this is here. And then we end up with 3 equals x, or x equals 3. Okay, x equals 3 is our answer. How do we know it's our answer? Well, we know it's our answer only when we plug in and are successful. Okay, therefore, if we go ahead and do plug in our 3 for x, that would be times 3. And this here would be times 3. Okay. And then we would have 100 plus 20 is 120, plus 30 is 150, plus 6 is indeed 156. Okay, so it checks out. We have x equals 3. Okay, now example 3 is going to be a little bit different, okay, because we are going to increase the dimensions of a square with a side length of x units, and another increase of length that is different than the increase in width. Okay, so a little bit different in that sense. Okay, so here you go. Example 3. The dimensions of a square with a side length of x units, okay, are increased. All right. In this figure, the indicated lengths are given in units, and the indicated areas are given in units squared. Okay? Alright, so your question here to answer is, what are the dimensions of the large rectangle in the figure? So this large rectangle right here, what are the dimensions of that larger rectangle? Okay, so go ahead and figure that out using that diagram. Okay, and come on back. Okay, so now again, step A asks, what are the dimensions of the large rectangle in the figure? Okay, what are the dimensions? And again, using your variables as needed. So the dimensions would be the length, and again, we've been talking about length this way pretty much. We've been talking about horizontal being our length, and vertical being our width. So far in this, we'll just keep that the same. But the length would equal x plus 3. Okay, and you can see that right there. Okay, you have x plus 3. You have an x here, and then you have 1, 2, 3. Okay, 1, 2, 3 there, x plus 3. Now width is going to be x plus 2, and that is shown that way, okay? X plus 2 there. So this whole thing, and you can see we have that. We also have the x plus 3 right there. Okay, so we have our length and our width. Moving on to B. So now use the expressions in your response from part A, okay, those two expressions that we wrote for length and width, to write an equation for the area of the large rectangle, where A represents area. Okay, so A equals. All right. So using those expressions, we have x plus 3, which is the dimension, the length dimension. It's going to be multiplied by x plus 2, which is the width dimension, which is how we calculate area, of course, length times width. All right, and that's just what we've done here. Okay, there's no mystery. It's just that now we have some unknowns. Okay, so x plus 3 times x plus 2 units squared. Okay. Now the next section here asks you to go ahead and use the areas of the section within the diagram. Okay, within the diagram, like we've been doing, to express the area of the large rectangle. And if you look at all those areas, all those parts within, all of these here, all of those, okay, we would come up with this here. Sorry, done this again. Let's just go and get to it here. Okay. And that would be A equals x squared plus 3x plus 2x plus 6 units squared. Okay, so let's just take a look at that again over. Oh, I didn't mean to do that. Let me go get that back, and let's go back here. Okay, and let's just erase all this so we can make some sense out of it. So here was the x squared. Okay, here is the 3x. Here is the 2x. And here are the 6. Okay, so that's where those came from. Okay, so as you can see, there's just two different ways to express the area, the way to calculate the area of that larger rectangle. Okay, one using the outer dimensions. Okay, the length times the width. And in this case, we've used actually the inside sections, okay, the individual sections within the rectangle. Okay, so what can be concluded from parts B and C? This might be a tough one to, because you don't really know quite what they're asking, but what they're asking is very, very simple, and very simply, x plus 3 times x plus 2 equals, or is the same as, x squared plus 3x plus 2x plus 6. They are one and the same in that you will, by plugging in a value for x, you will get the same answer on the right side as you will on the left side. Okay, so those are expressions are equivalent expressions written differently, but if we do take a look at it, we can use the distributive property. Okay, and we've only used the distributive property. I'm just going to show this to you just real quickly because I don't want to get too much involved in it. But we've used distributive property in the past. We've done something like this. So if we had 3 and then parentheses x plus 4, where we do 3 times the x, 3x, and then plus 3 times the 4, which would be 12. Okay, so we can distribute that 3 right here, and we would get this. Now, when you're doing something, when you are doing the same, you can distribute with these two expressions as well. So if we had x plus 3, and then times x plus 2, we're just going to go another step. So we're going to go, we'll just distribute the x first. Okay, so we have x times x is x squared. Okay, plus, and then we have x times 2 is 2x. Okay, so we're done with that. Now let's go and work with the 3. So now we have 3 times x is 3x, and then 3 times 2 is 6. Okay, and you'll notice that is that. Okay? Well, these have just been moved around, but doesn't matter. Doesn't make any difference value-wise for the worth of those two expressions. But yeah, there we go. So you can see we have proven that this equals this by just distributing, using the distributive property right there to come up with this expression. All right, and that is really the real fun part, I think, of algebra. So here, just summarizing this lesson, the properties of area are limited to positive numbers for lengths and areas. Now, we didn't actually, I'm surprised that's one of the major points here, but okay, well, you know that they're limited to positive numbers. I mean, it just makes sense. Again, I'm not sure why that's in the lesson summary, but because we can't have negative numbers for lengths. We just don't have negative lengths. Okay, something can't be negative 2 feet long. All right, it's just we don't work that way. We work all in positives for lengths and areas. Okay. All right, and the properties of area do support why the properties of operations are true. Okay, and again, we did not. Maybe that came across in some way, but I guess we're talking about properties of operation, and in this case, we're talking pretty much about that distributive property. And even though it was just the last thing we did here, we showed how these two are related in terms of area, how they are related through the distributive property here. Okay, and anyway, I guess we'll be looking at lesson 22 to go into more detail with these concepts. For now, just go ahead and get your problem sets done, and come on back next time.